We are doing chapter 3, section 6, derivatives as rates of change. So we need to start transitioning to practical application. What do derivatives mean in real life? How does that connect to real world problems? So you'll notice as we move on in this year, it's going to move from formulas and mathematical things to applications. And so if you don't understand, if you just memorize formulas and you don't understand what they're saying, you're going to have a problem transitioning to meaning in real life. And half the AP test are FRQs, which are word problems. And even within the multiple choice, there are problems that are basically word problems where you have to understand this in the concept of real life situations. So derivatives as a rate of change. So the first example is position. And every year, there's always one FRQ that's all about position, acceleration, and velocity. And so that's what we're going to be focusing on here. So we are doing two-dimensional motion, meaning you can move either left or right. So there's S sub 0. That's like your starting position. Maybe it's your home. You're starting at your home. And as you move right, that means your position or distance from home is increasing. And so that's your distance from home. That might be to the east. And if you go to the negative, that's to the west. So you have two directions of motion. And so this graph here, this is your position. So this means you're at home. This means you're moving away from your home towards the east. All right, if you were going down, you'd be moving away from your house towards the west. And this is time. As time goes on, what's happening to your position? So if you look at the graph of the black line here, so at time 0, well, the graph doesn't actually continue. It looks like you are west of your home, okay? As time moves on, you're walking towards your house, and at this point, your position, S, is 0. That means you're at your house. And as time goes on, you're moving away from your house, farther, 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 farther. And at this time here, you are this far, this distance, away from your house. So as you move up, you're moving away from your house. But as you move to the right, time is passing on. So that's the interpretation of this graph. So if you notice, your distance from your house is increasing really fast there. But here, the distance from your house isn't increasing very fast. So you can see there's a change in how fast you're moving, and you have to contemplate that. So in this amount of time, you moved that far. So that's your delta position, your change in position increased a lot in a short amount of time. Now, if we use that same amount of time here, if you look at the graph, your delta position over your delta time, your position changed very little compared to here. That's a big change. That's a small change. If your position changes a lot in a given amount of time, you were moving on the faster side. But if your position here didn't change much, in this time period, you were moving much slower because you didn't go as far. So you need to start seeing this graph for what it's telling you. Now, they're going from time A to A plus delta t. That's just a change in time, where the distance from here to here is delta t, as they labeled here. Okay, so you have a function, f. So the equation of this graph is f of x. That is your equation. Oh, they actually have it right there. So that's your position from the graph. At time A, your position is there, and that would just be f of a. And if you add delta t a set amount of time, your position at a plus delta t is going to be f at a plus delta t. So what's the position change? You take this position minus this, and that gives you this distance, which they have here. And they labeled that as delta s for change in position. And if you want to know the time distance from here to here, you take that, subtract that, and you end up with delta t. So if you were to divide delta s by delta t, that's the slope of this green line. Okay? The slope of that green line. And they don't write it down here, but I'm going to write it. So with this green, I'll get a darker green. So the slope of the green line would be delta s over delta t, which is f at a plus delta t minus f at a over delta t. Now this is your average rate of change. It's the slope of this line. So average rate of change. That's your, in this case, your average velocity. The secant line gives you average velocity because it tells you over this large amount of time how far you went compared to that time. It's not at every instant, but overall your average rate of change. So this is your formula for average velocity, but let me change the units. If we were to change this to B, whoops, I don't know what just happened. I'll do it in a different color like blue so you can see. If we had, instead of A and B, this would be f of A and f of B. Your delta S in this case would be f of B minus f of A. And your this delta T in this case would be B minus A. So in the blue case, it's exactly the same. It's just different labeling. You would get f of B minus f of A over B minus A. So it's the same thing. These two formulas are one and the same. The only difference is instead of A and B, we've defined this distance to be the change in time delta t. So we're going to get A and A plus delta t. That just changes the labeling. So both these formulas are exactly the same. Average rate of change is the change in the position over change in time over a large period of time from A to A plus delta t. So these give you the average velocity. Now we did this in 3.1, the definition of the derivative, but now we're doing very specifically for velocities. We actually did that in 3.1 also. We'll do other applications. So what's happening here, if we chose delta t to get smaller and smaller and smaller. In other words, this point Q, it's got to freeze in my screen. I hate when that happens. Let me see if I can get rid of that. Okay, so as Q moves closer and closer to P, if you draw all these secant lines, you see them drawing it as the point gets closer and closer, you will notice these green lines are approaching the tangent line. So the tangent line is a line tangent at point P. So here's what it's saying. As this delta t gets smaller and smaller and smaller, as Q is moving this way, the slope of the green line, the average rate of change, is approaching the slope of the tangent line, which is an instantaneous rate of change. So that's why they have this limit as delta t approaches 0. But delta s over delta t is this slope, so they have this formula. So by definition, the derivative is the velocity. So what is velocity? So if you see a car and it's going by you, how do you know if its velocity is high or low? Now, subconsciously, I don't think you really think about this, but it's the distance it moves in a given amount of time. If it moves a large distance in a given amount of time, you say, man, that thing's going fast. Its velocity is high. But if you watch it and in 10 seconds, it moves like 5 feet, you're like, man, that thing's slow. Its velocity is very low. So velocity is the change in position over change in time. Change in position over change in time. So velocity is change in position over change in time. This is average velocity. But when you take the limit, that becomes instantaneous velocity. So the derivative is the velocity. The derivative of the position function is the velocity. You need to know that. Now, I'm going to write this as a blue function. What is velocity at a specific point? It's the limit as b approaches a of f of b minus f of a over b minus a. It's the same formula here, except I'm using a's and b's. Now, you could also do x's and y's if you wish, or not x's and y's, sorry, x's and a's. So velocity, it'd be x here, and x here, same thing, just x's instead of b's. Or you can use t, because it's as time approaches a. So there's a lot of ways we can write that. So you need to be comfortable with variables switching. They're just variables. It's just what you decide to call it. So we could call it velocity at time t as the time t approaches a. But this is nothing new. All we're doing is saying instead of x's and y's, think of it as position and time. So here's what you have to understand. The slope of the tangent line is the rate of change at p, the instantaneous rate of change. At the instant of time here, at that specific time, you have the instantaneous rate of change known as the velocity. The velocity is known as the instantaneous rate of change. How do you find that? I told you in 3.1, you look at your speedometer, and that's how fast you're going at that instant. If you look at the slope here, you can see it's a lot slower. The car was going a lot slower at that point, like we talked about earlier. It's not traveling as far in the same given amount of time. So the slope, if you just look at tangent lines, wow, that's a high slope, high velocity. Slower slope, lower velocity. Very low slope, very low velocity. That's the connection you need to make. All right, excuse me. So that's derivatives as a rate of change. So we're just giving you some formulas. Average velocity is that, or f of b minus f of a over b minus a. Or I should use time for t. Let's do that. It doesn't matter what you use. So it's just your basic average rate of change formula. We'll do some examples in a second. Instantaneous velocity is the derivative. That's what you have to know. The velocity formula of a function is the derivative of the position function, assuming f is the position function. So how fast your position changes, that's what this is saying, is the velocity. That's all I have to say about that. Let's read this example and walk through it. So you have a police car. Assume the police station is located along a straight east-west freeway. At time t equals 0, which is noon, the patrol car leaves the station heading east. So east is the positive distance away from the station. So they're traveling east and west on a freeway. So if I were to draw that, there's a freeway traveling east and west. 0, that's where the police station is. And as you move to the right, it's farther east or a positive distance from the police station. If you move to the left, it's going to be a negative distance from the police station. So at time t equals 0, they tell us it's at the police station. So that's why here, for t is 0 right here, the position is 0. Starting at the police station. That's all that's saying. So you have a position function. This function is s is f of t. F of t, which is this graph here, this is a graph of f of t, gives you the position of the car at different times. So after 30, is that minutes? I'm assuming it's minutes. Is it hours? No, it's 3.0, sorry. After 3 hours, the police car is 20 miles east of the police station. At 20 or 2 minutes, 2 hours, hours, the car is 80 miles from the police station at 2 hours. At 1 hour, the car is 60 miles from the police station. Now at 3.5 hours, the car is 20 miles to the west of the police station. So this is it. It got to the police station here. Now it's going the other direction. So that's everything that's kind of going on there. Okay, so part A. Describe the location of the patrol car during the first 3.5 hours of the trip. So basically, you could say this. As time goes on, it's traveling farther and farther east up until 1.5 hours. At that point, look, the position stays 80 miles away. The car is not moving here. From 1.5 to 2 hours, the car has stopped moving. I'm assuming getting a break, eating, possibly donuts or a lunch, something. Or maybe there's an accident, it pulled over and is helping at the accident. For some reason, the position does not change for a half hour. The position is always 80, so it's stopped. And again, the slope of that line is 0. The slope of that line is the velocity. The velocity is 0. Now, from here, the distance from the station is decreasing. It's moving back towards the police station. After 3.25 hours, it's at the police station. Then it moves past the police station and it moves 20 miles to the other side of the police station. So that's part A. Part B, calculate the average velocity from noon till 2. Remember, noon is t equals 0. So they want t equals 0 to t equals 2. So B, we did A, average velocity is, and it's going to be f of, that's a 2 by the way, f of 2 minus f of 0 over 2 minus 0. Well, f of 2 is 80. I can do that. And f of 0 is 0. I can do that. So that'll be 40, and the units are miles per hour. So the average velocity for the first 2 hours is 40 miles per hour. Part C. Calculate the displacement and average velocity of the car between 2 to 3:30. Okay, displacement is a new word. I need to define that. Another word for displacement is the change in position. Change in, let me erase this stuff here, position. It's a word that will appear on an AP test. So understand what it is. So displacement is going to be, and it's going to be the position at 3.5 minus the position at 2. So all it is the change in position. At 3.5, we have negative 20 minus, and f at 2 is 80. So I'm going to put in 80 there. That's going to be negative 100 miles. So the displacement, it moved east 180 miles, or the position changed, excuse me, not 180, 100 miles to the east. That's the displacement. And average velocity, so average velocity is the same formula. It's going to be f at 3.5 minus f at 2 over 3.5 minus 2. Well, we already did the top. That's negative 100 over 1.5. And that's our answer. Do I need to work that out? I'm going to leave it like that, or I can ask Siri. 100 divided by 1.5.
It's about 66.6666.
So the average velocity would have been negative 66 2/3. All right, that is part C. Part D. Okay. This one is going to be more of looking at the graph and understanding instantaneous velocity. What is instantaneous velocity? It's how fast it's moving at a particular time. Do you guys remember? You can pause the video and think, how do I find instantaneous velocity? All right, think about that, get an answer, and I will tell you what is the answer. All right, hopefully you said the slope of the tangent line. So when it travels east, east is to the right. So that's going to be during this time. So at what time is the instantaneous velocity the greatest? I'm looking for the steepest slope. It looked like it's kind of flat there, steeper, right about there to me, because it is flatter here. So this is a guess. I'm thinking somewhere around 3/4 of an hour later. That's just a guess. So I would say for part D, my guess is t equals 0.75 hours. But that's an approximation. You guys can have a different answer if you think differently. So that is my answer. So somewhere, this is 12, 12:30. This is 1 o'clock. Somewhere between 12:30 and 1. Looks like the answer. And part E. At what time is a patrol car at rest? We already talked about that. If it's at rest, if the velocity is 0, the position doesn't change. And that's going to be from 1.5 to 2 hours. So hopefully that makes sense. You might want to listen to that again and have it make sense. So I need to get a concept. This is an important concept for you to know. What is speed compared to velocity? They're two different concepts. So velocity includes a magnitude and direction. A magnitude and a direction. How do we display that? Well, the direction is going to be positive or negative, right or left, or up or down, depending on what's going on. So when you have a velocity, they're going to tell you which way you're going, right or left, up or down. And it's going to tell you how fast you are going, 50, 60, 70. So speed only cares about magnitude. Okay, very different. That's how that definition is used in calculus. Speed doesn't care about the direction, only how fast you're going. Velocity is going to be how fast you're going and what direction you're going. So if you know that, how do you find speed? Speed is the absolute value of velocity. The absolute value strips velocity of its direction. So that's my little spiel on speed that you have to know, okay? Now we have one more concept. That's not the line I want. What is acceleration? So you need to know what is acceleration. Now think about it. When you see a car drive by, if it's going super fast, do you say, man, that car is accelerating fast? No, you wouldn't. You say its velocity is fast or velocity is high. So what is acceleration? This is how you measure acceleration. If a car is not moving and all of a sudden, vroom, it's going super fast, and then, man, that car accelerates fast. I want a car like that. But then if you see a car that's not moving and then slowly it goes faster, then faster, then faster, you say, man, that car is it doesn't accelerate. It doesn't have much power. And most people want a car that speeds up fast. So you want a car with a big engine or a high horsepower engine. You want your GTRs and your Vets or whatever car that has high performance engines. And you say accelerates fast. So what is acceleration? When your velocity changes really fast, that's your acceleration. So acceleration is the rate of change. Comparing what? The rate of change of velocity. Ooh, sorry, I ran out of room. How fast your velocity is changing. If a car has high acceleration, the velocity is changing really, really fast. So you got to understand that concept. Acceleration is the rate of change of velocity. So we have some formulas here. So assuming f of t is your position function, you already know this, the velocity function, I'm going to write it differently here. The velocity function is the derivative of the position function. You have to know that. So speed, I already told you this earlier, is the absolute value of velocity. So if you want speed given a position function, you absolute value the derivative of your velocity. Now here's the one that's important, acceleration. So I already said acceleration is how fast your velocity changes. So, well, they have it nicely here. It's the derivative of the velocity, the change in velocity over change in time. When you see a derivative, this is change in velocity over change in time, but in the derivative, delta t is approaching 0. It's infinitesimally small. So that's the difference between delta v. So if I had a delta v over delta t, let me get rid of that. That's average rate of change. Delta v over delta t. That's average rate of change. Over a large period of time, how much did the velocity change? That's average rate of change. But we are looking at instantaneous rate of change. So when you have a little d and a little d there, that tells you at an instant. Now, how does that work? What is velocity? Velocity is the derivative. So if we take the derivative again, that's the second derivative. So here is the next major thing you need to know. Acceleration of a function is the derivative of the velocity, which is the second derivative of the position. So in other words, if you have the position function, you take the derivative twice to get acceleration. But if you have velocity, you just take the derivative once to get the acceleration. Because, remember, acceleration is how fast your velocity is changing. It's how fast velocity is changing. But dv dt is the derivative of velocity. So all those you need to know. All these things I'm talking about can be quiz questions. Make sure you know these. I have two more examples? 3 more? Okay. Hopefully this video is not going to be too long. I want to wrap this up quickly. Let's look at this question. What do they tell us? We have a position function. Here's our position function right there. And here is our time frame. All right, let's read the question. Graph the velocity function on the interval from 0 to 5 and determine when the object is stationary, moving to the left, moving to the right. Oh, so we have to find the velocity function and graph it. So the velocity function is the derivative of the position function, which will be 2t minus 5. All I did is took the derivative of that, 2t minus 5. So if I were to graph that, I'm going to do a rough graph. Here's minus 5. And if you graphed it, it should look something like that. It's a line, slope of 2, and a y-intercept of negative 5. So I graphed it. Determine when the object is stationary. Moving left, moving right. Okay, process this. When is something stationary? When its velocity is 0. When v of t equals 0, t equals. When is the velocity 0? Right there. All right, I need to figure this out on the graph. On the graph, I guess I just do this. V of t, 2t minus 5 equals 0, when 2t equals 5, or t equals 5 over 2. So 2.5 units of time. Is it seconds? Yeah, seconds. That's when it's stationary. That's part A. So this is the velocity function. I graphed it here. It's stationary at 2.5. When is it moving to the left? So if it's moving left, that means, hold on here, moving left. That means its velocity is negative. When is the velocity negative? The velocity is negative when in this region. So that's going to be from time 0 to 2.5. And when is it moving right? It's moving right when the velocity is positive, and that's in this region, and that's going to be from 2.5 to 5. I have to stop at 5 because that's the end time. I can do a closed bracket there. So that is my answer for A. B, graph the acceleration function. Well, how do you find the acceleration? We learned that the acceleration is the derivative of the velocity. Well, what's the derivative of this function? It's just 2. So we know the acceleration is 2. That means every second, or let's see, every second, the velocity changes by 2. So every second you move over, the velocity is 2 bigger, 2 to 1. 1 second, the velocity increases by 2. That's what that means. Graph that. So I'll graph that in red. We'll do 2 there. That's the acceleration function. In part C, describe the motion of the object. So you can say it constantly accelerated at 2. The velocity, I don't know how to describe. I'll do this. So look, here's the starting position. It's moving. Okay, the position is becoming more negative. That means it's moving to the left. So it's moving to the left for the first 2.5. Looks like 2.5 minutes. Or seconds, sorry. And then for the next 2.5 seconds, it's moving to the right. So it moved away from the starting position for 2.5 seconds. It turned around and moved back. And after 5 seconds, it was at the starting position of 0. So that's what I'm going to say. That's the story I'm using, and I'm sticking with it. Okay, now it's another problem, but the difference here, it's being vertically upward. So in this case, you have a 0, up is positive, and down is negative. Now, in this case, it can't go down. Oh, wait, let me see. Can it? Oh, it's on the bridge, so it can actually go below the bridge. Actually, let me read this. Velocity 64 from a bridge. Okay, it's actually the ground is 0. Position is measured height above the river. So you can't have a negative height, actually. Let me erase that, because then that means you're underneath the river. And is that possible? I don't know. Let me go ahead and redo this. So this is a river. And this function is the height above the river. So if you plug in a 0 here and here, your height at 0 is 96. You're starting from a bridge 96 feet above the river. That's what it's talking about. And you threw it up at 64 feet per second. So here is the position function. Find the velocity and acceleration functions. Okay, you should be kind of getting this. The velocity, we learned, is the derivative of the position. So that's going to be negative 32t plus 64. I just used so the 16 stayed, the 2 came in front, and I decreased this by 1. So that's why it's a 1. And the 2 and the negative 16 make a 32. And then this is the first power. I move it in front, so I have 64t to the 0. But t to the 0 is just 1. So that is my velocity function. Acceleration, you should know, is the derivative of the velocity. So I take the derivative again, I just get negative 32, and that is my acceleration function. Part A is done. What is the highest point above the river reached by the stone? Here's where you have to think. If you throw a stone up, it goes up, and then it comes down, and it hits the river. Okay? At the highest point, you have to think, what's true at the highest point? I claim that the rock stops moving up. I claim at that highest point, that at that point, the velocity is 0. What it's really asking for in part B is asking for when is the velocity 0. So part B, when is the velocity 0? Well, the velocity is negative 32t plus 64. I'm going to subtract 64 from both sides. Then I'm going to divide both sides by negative 32. And I get positive 2. So 2 seconds later, it's at the highest point. And part C, what will the velocity be when it strikes the river? How do I do that? So what do you know at the point when it hits the river? Do I know the time? No. Do I know the velocity? No. Do I know the acceleration? You actually do, but that's not going to help you. The acceleration is always negative 32. So the only thing you know is the position. The height is 0. So you would set your position function equal to 0, s sub t, which is negative 16t squared, plus 64t, plus 96 equal to 0. You'd have to solve that. I wonder if I can factor and cancel that. Let me take a look here. Do I have to use a quadratic function, or can I solve that? Let me think about this. Hold on. Let's see. Yeah, I can. Let me factor out a 16. I think I could do that. Is 16 times 4? Is that 64? 30, yep. And is it 6? 6 times 16 is 30. Yep, that works. So I factor this. Is it factorable? It might not be. I might have to use a quadratic formula. 3 and 2, yeah. We're going to have to use a quadratic formula. I wish I didn't have to do that. But if you do use the quadratic formula, you'll find your t is approximately 5.162 and negative 1.162. Well, negative is ridiculous because I can't go backwards in time. That's wrong. So it's at t is 5.162. So what's the question asking for? What was the velocity? I know the time when it strikes the water. So to find the velocity, I plug in 5.162 into the velocity function, which I have here. And if I do that, it comes out to be approximately negative 101.184. And why negative? Because it's moving down. Down is a negative velocity. So that is C. And let me throw out one last thing. I'm just going to we're not going to do a lot here. But what if it's not position? What if it's the weight of a bird? The weight of a bird. Let's evaluate what's happening if it's the weight of a bird. So this is time in days. I don't know. Let's say this is 30 days later. So if you drew a line here, a tangent line, or excuse me, secant line, let's do it with actual color. I'll do it in blue. Blue, blue, blue. If you found the slope of that line, that would be w of 30 minus w of 0 over 30 minus 0. That would be 100 minus 0 over 30. So that's, I'll just leave it, 100 over 30 grams per day. That's the average rate of change. So this is about 3 1/3, I believe. So that means on average every day the bird increased in weight 3.5 grams, the baby bird. Okay? So my question is, was it gaining 3.5 grams every day? No. Each day, whoa, what just happened? I lost my notes. There we go. Each day, it was different. And how do I figure that out? So when it was first born, look at that. It's the slope of that is the instantaneous rate of change. How fast its weight is changing that day. It's really not changing. But as time goes on, its weight starts to increase faster. Look. And at this day, its weight's really increasing. On this day, the bird's weight is super fast increasing. It starts to slow down. As it gets older, you don't gain as much weight. Well, hopefully you don't. I had that problem. I was gaining weight faster when I was older than younger. But hopefully for this bird, eventually it's going to stop growing. And that's what's going on. So first, it doesn't grow much. The bird starts to get bigger, becomes adult, growing super fast, and then it just stops growing in weight. So that's what's going on there. So it's not always velocity and acceleration and speed. Sometimes it's talking about other things. How fast snow is falling, how fast rain is collecting in a barrel, how fast the economy is growing, how fast are subscriptions to Netflix growing, what is the maximum of that. So there's a lot of applications to this rates of change. It's not just position and time. It's a lot of other things, and this is an example just to kind of get your brain going in the right direction. All right, that's it for this video. Bye-bye.